When I say that the inductor is in continuous conduction mode, it means that the current will be flowing from this inductor throughout the time. So what does this imply? This implies that a pair of diode would be conducting at any given time. Okay, if this inductor is if the current is continuously passing through this inductor, this implies that one of the pair, either one of these pairs will be operating, whereas they will be operating, these pairs will be operating continuously, whereas in the previous case we saw that these diodes, their conduction time was very small. When we used capacitor as a filter over here, in that case, and there was no inductor in our circuit, we were using capacitor as a filter. In that case, these diodes were operating for a very small time period, due to which the peak value of the current from these diodes were increased. But now in this present case scenario, when we are saying that we are using inductor as a filter and it is in continuous conduction mode, due to which a pair of diodes will be continuously conducting, at least one pair will be conducting at any given time. So the peak values should reduce theoretically. So let's see whether this will happen or not. And next thing is that I am considering that V1 is equal to Vs. The voltage obtained at this point over here, this is to this value I am calling V1. Whatever the value of the this sinusoidal source is obtained at the same is obtained at with the transformer 1:1 is obtained at the secondary of this transformer, and the same is being obtained over here. Now, say I have considered that there is no drop across the voltage across the inductor, and the average value of inductor is 0. In that case, V1 average is equal to V0 is equal to 1000 volt. When there is no voltage drop across this inductor, the average value of voltage across this inductor is 0. So the same should appear on output, and it was 1000 volt. Fourier series of a full wave rectifier can be calculated using the basic definitions of this Fourier series. That is, it has this voltage has a DC component and the sinusoidal terms. When these are calculated, the final result obtained is VLT is equal to 2 Vm by pi 4 Vm by 3 pi cos of 2 omega t minus 4 Vm by 15 pi cos of 4 omega t. Okay. So this VLT, this is basically, this is what to this term, this is the output of the rectifier, and I have called this as V1. This is the Fourier series of the full wave rectifier. The output of the full wave rectifier will I have denoted that by V1, and this was the generic formula that I have they have all it has been calculated in your book. So if anyone is interested in knowing how can we calculate this Fourier series, it is in your book of M.H. Rashid. This first term, this is the DC component. So 2 Vm by 3 pi is equal to VDC, and I know that the output voltage is 1000 volt. Average value of voltage at output is DC, and it is 1000 volt. Using that, I can calculate the maximum value. 2 Vm by pi, in this expression Vm is the maximum, the peak of the voltage. VDC is the average value. Using the Fourier series, in Fourier series of full wave rectifier, this first term was representing the DC component. So by comparing these values and equating it equal to the known value 1000 volt, we have now determined the peak of this waveform that will be obtained at output of rectifier. Now this Vs RMS is equal to whatever the peak value divided by square root 2 is Vs RMS, and this is the rating of the same is the rating of the transformer. This is the rating of the secondary side of the voltage of secondary side of transformer in RMS. Okay, so let me repeat this again. We were only known this thing, that the output DC voltage obtained was 1000 volt. By using the Fourier series formula of a full wave rectifier, we calculated the peak value of this output of the full wave rectifier. Once we had that peak value, we divided by square root 2, and from there we can have our RMS value. So the same was being supplied by the transformer, and these diodes are in parallel with this transformer, so they should have same rating. Hence, its RMS value is whatever the peak value was divided by square root 2. Now, if I want to calculate the voltage rating of these diodes and the other thing, so the first one is this is basic. See that this peak is different. This peak is the output peak voltage, whereas this peak is the voltage that was of the rectifier output. If this is the output of rectifier obtained at this point will be like this, from 0 to its peak value, whatever it is, Vm, and has some and after passing through this inductor, these ripples were reduced, and we obtained a waveform like this. Okay, so ideally a waveform like this, which had an average value of this V naught, which is, and this is appearing across this load, and it is 1000 volt. Okay, so this peak value that I am talking about, this Vp, this is the peak value with respect to this average value at obtained out output. This peak value has some ripple in it, and that ripple is between 10 plus minus 10 volt. So 10 volt on the upper side, it makes it 1010. When we will consider a ripple of minus 10 volt, in that case our average output voltage will drop from 1000 volt to 990 volt at that instant. And so so basically my output is between 1010 volt and 990 volt. I think it should be clear by now that this V peak, this is basically the output peak voltage, and the output peak voltage across the load, and this Vm, this is the peak voltage of the output of the rectifier. Now I have to calculate the peak inverse voltage of the rectifiers, and whatever the value of the voltage, the peak value that will appear over here should be the peak inverse value of these diodes. Whatever voltage come across this over here should be the peak inverse value of these diodes. Therefore, the peak inverse value of these diodes is 1570 volt, and the RMS value of these diodes should be 1570 divided by square root 2, that is 1110 volt.